Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
In the PE 300 series of the video library, which deals with well completions and stimulation, we have presented the basic concepts of perforating, acidizing, and fracturing. This module will present the well completion technique of sand control. The production of formation sand has proven to be a serious problem. It can result in unacceptable reductions in rates and damage to the surface and downhole equipment. Sand control measures may include restricting production, optimizing perforating techniques, and using mechanical or chemical methods to create a highly permeable downhole filter. One common sand control method is the gravel pack. The term gravel pack can be misleading, since it often refers to a uniform silica sand, such as the 2040 mesh sand used in hydraulic fracture stimulation. When packed against the formation, this type of sand serves as a retention-type filter. It is estimated that billions of dollars are spent annually on sand control completion, repair, and technology. Unlike fracture stimulation, which is employed on less productive wells, sand control is often a necessary practice employed on many prolific wells throughout the world. This module is intended to enable engineers and other technical specialists to understand sand production problems and solutions. In the first unit of this video, we'll discuss sand control fundamentals and basic methods. In Unit 2, we'll discuss the various mechanical methods of sand control and gravel pack design. We'll also consider installation procedures. And in Unit 3, we'll provide an on-site review of the procedures and equipment used in gravel pack operations. Upon concluding the module, the viewer will be able to design a sand control program and specify the necessary sand control equipment. Let's start by considering the effects of sand production.
Wells that require sand control are those in sandstone reservoirs in any area of the world where damaging quantities of sand are produced. This tendency may be displayed by reduced well productivity, repeated bridging in the tubulars, or by serious erosion that interferes with the operation of downhole or surface equipment. Temporary problems, such as those experienced by many wells as a result of cleanup sand or long-term fines migration, will not be discussed in this video program. The distinction between acceptable and damaging levels of sand production varies among operators and areas. For example, in the U.S. Gulf Coast, 600 pounds of sand per 1,000 barrels, 1.64 kilograms per cubic meter, is generally considered the limit. In parts of the world experiencing greater production rates, pressures, and operating costs, an acceptable limit may be set at 10 pounds per 1,000 barrels, 28 grams per cubic meter. If the production velocities are very high, such as in prolific gas wells, sand production in excess of just 5 pounds per 1,000 barrels, 14 grams per cubic meter, may be overly damaging. Although these values are approximate, they are intended to illustrate that any well that experiences sand problems must be considered a sand producer. And sand production is costly. The continual influx of small quantities of sand may not immediately impair the production equipment or well productivity, but certainly could result in major problems in the future. Erosion may result in the failure of the casing or liner, or the induced formation cavities may collapse. Remedial work of this nature is very expensive and often unsuccessful.
The potential economic consequences of the decision whether or not to install sand control can be great. This decision must be based on many complex combinations of physical, economic, and experiential factors. Let's first consider the physical factors.
The classification of sandstone reservoirs prone to sand-related problems can be determined qualitatively by a combination of factors, such as analogy to geologically similar areas, visual core analysis, log interpretation, well tests, and field experience. All of these can indicate potential sand problems.
The well site geologist has traditionally classified sandstones based on visual and field tests. These tests, described in your manual, are used to categorize sandstones into one of 5 groups: unconsolidated, partially consolidated, friable, consolidated, and hard. Sand production problems are mainly associated with the first 3 groups.
In 1970, Van der Vlie introduced the concept of classifying sandstones according to the Brunel hardness number, or BHN. This simple lab procedure, requiring a core sample, has yielded good correlations with elastic moduli and sand strength. In the Brunel test, a steel ball is forced into the sandstone sample. The amount of force required to crumble the sample is measured in kilograms per square millimeter. This measurement is then compared to the Brunel hardness scale. Of the 5 categories of sandstones, unconsolidated sands are responsible for the majority of sand-producing problems. These sands are typically uncemented, have a Brunel hardness of less than 2 kilograms per square millimeter, and, unlike the other sandstones, are usually found at depths of less than 8,000 feet, 2,400 meters, in relatively young formations, Miocene to recent. Partially consolidated sands, having a Brunel hardness of 2 to 5 kilograms per square millimeter, and friable sands, having a Brunel hardness of 5 to 10 kilograms per square millimeter, are considered partially to well cemented and may cause varying degrees of sand problems over the producing life of the well. Although the in situ stresses present in unconsolidated and partially consolidated sands do not conform, in application, to the existing theory of rock mechanics, the principles are useful in developing other predictive tools. Sand production occurs when destabilizing forces exceed the strength of the in situ stresses and cementation. The destabilizing forces are due to production, excessive pressure gradients across the sand face, and high or increasing water saturations. These factors may be controllable, such as excessive production rates, or uncontrollable, such as depletion or water drive. For example, to determine the effects of changing water saturations, rock samples are taken from the completion interval and sent to the lab for analysis prior to completion work.
Typically, we receive samples from all over the world, and one of the questions that we're asked is, do we need to gravel pack this well? In the case of this sample, you can see it's very unconsolidated. And the answer is obvious. Yes, this well will need to be gravel packed. The hard part comes in when you get a sample like this that's basically consolidated, and we'll have to have additional tests run to determine what's going to happen to this well after it's put on production. A quick and easy way to determine this, one of the methods that we use most frequently, is a disassociation test where we'll soak this sample into different fluids. For example, this is bland oil. When the well is first put on production, that's basically what it'll see, oil production. As you can see here, this sample has stayed associated and has not fallen apart. However, that's not the case with water production. As the well depletes and the water production increases, this is the kind of a scenario you're going to see out of this sample. This was also consolidated when we started, but it's totally disassociated at this point in time. This is 2% KCl. Similar thing happens in 3% ammonium chloride water, and also in a standard API brine. So what this has told us here is, although this sample appears to be consolidated, if they expect any water production whatsoever, the odds are good that they're going to have to gravel pack.
Since 1970, considerable research has been conducted on the subject of rock mechanics as it relates to sand production. However, success has been limited, with no universally applicable method considered proven. Possibly the most common method of sand control analysis is to compare similar wells.
The factors that are usually compared are porosity, permeability, geological age, formation depth, depositional environment, fluid type, and primary cementation material. Historically, reservoirs that have sand problems are highly porous, highly permeable, young, shallow, dirty, highly water saturated, and poorly cemented. Let's look at another analysis method, one that relies on core samples recovered from the subject well to give an indication of potential problems. Obviously, if the recovered core falls apart as it is retrieved, or the sand grains can be rubbed off or broken, the chances of sand production would be great. Care must be exercised during coring operations to employ techniques that ensure the recovery of good samples. You may wish to review the special coring and core handling techniques presented in PE 405, Core Analysis, and GL 303, Sample and Core Handling and Analysis. Ideally, in addition to visual observations, core analysis should include thin section studies, SEM studies using a scanning electron microscope, core flow tests, rock compressive strength tests, and Brinell hardness measurements. The data obtained from core analysis can quantify formation and rock properties. These can be compared with existing wells or used to define reservoir characteristics for future reference. Geophysical log analysis provides another method of studying sand production tendencies. A great deal of effort has been spent in this regard. Several companies have developed proprietary in-house techniques, and, fortunately, many papers have been published on the use of sonic and density logs to evaluate sand problems.
Two commonly used sand production indicators using geophysical log analysis are a technique published by Stein and Hilsche with Mobil in 1972 and a method developed by Tixier in 1975. The technique presented by Stein and Hilsche is sometimes reduced to a simple rule of thumb. Any zone with a sonic transient time in excess of some locally determined threshold will produce sand. This threshold usually ranges from 95 to 110 microseconds per foot. The Tixier method of indicating sand production tendencies utilizes log-derived factors of shear modulus divided by bulk compressibility. This method has proven acceptable provided depth versus sonic trends are similar to those experienced in the U.S. Gulf Coast. The threshold above which sand production should not be expected is approximately 0.7 to 0.8 times 10 to the 12th psi squared in the U.S. Gulf Coast. The Stein-Hilsche and Tixier methods are used to generate a sand failure envelope to indicate when sand production might occur.
Schlumberger analyzes sand strength by using sonic and density log data and a failure envelope based on Moore's circle. This information is presented as a sand strength analysis log that can indicate potential sand-producing intervals. This technique is most effective when complemented with additional information, such as field histories. Probably the most consistently accurate method to determine whether sand problems will exist at a given reservoir pressure is a properly conducted production test where sand cut, production, and bean size are recorded. This type of well test should have sand detection equipment at the surface and downhole if possible. The test should consist of a step rate test for extended flow periods. Depending on well deliverability and indications of potential sand problems, a step rate production test may last from several days to several weeks. The duration of the test should be sufficient to confirm whether or not the sand influx would persist or decline to an acceptable level without costly sand control measures. During the flow test, excellent data may be obtained about sand production characteristics, produced fluid properties, and pressure transient analysis. You are encouraged to review PE 406, covering the analysis of produced fluids, and PE 401, 402, and 403, regarding pressure transient testing.
The engineer should analyze new wells, whether development or exploratory, in order to determine the potential for sand problems. Existing wells usually have accumulated data that can form the basis for the decision to use sand control methods. The engineer, however, must study the effects of depletion, changing fluid production, both quantity and composition, completion methods, and other variables influencing sand production over the life of any subject well before making the final decision. Once a decision has been made to employ sand control methods, the wide range of techniques must be evaluated, from maintaining production at a rate that will limit sand production to a more sophisticated consolidation process whereby the sand grains are cemented or bonded together within the formation.
However, before sand control techniques are employed, it is critical to use completion techniques that will minimize the tendency for sand to be produced in the first place. Poor completion efficiency will result in near wellbore damage and increased drawdowns, and that can lead to possible sand movement. The main aspect of completion efficiency is to employ perforating techniques as described in PE 303, perforating. In certain areas, rate control and the natural arching of formation sand can be effective sand control methods. However, the rate necessary to control sand production is often very low and thus adversely affects the economics of the well. As shown in this production test, production had to be reduced significantly to obtain an allowable sand limit. The choke beam that was selected only allowed acceptable sand production levels for 2 weeks, after which the well needed to be beamed back further. Based on this data, it is unknown whether the apparent natural arching effect displayed by this well will stabilize on this reduced choke. Only time will tell. However, if this beam size allows acceptable economics and sand stabilization for several years, then this method will have proven more favorable.
Field observations and research published by Dr. Kohlhaas at the Colorado School of Mines indicates that this arching process does work, in that, first, slow bean-up should be used to maintain arch stability after any shut-in period. Second, arch stability increases with confining stress. Third, fines migration and water production are major destabilization mechanisms. And finally, fourth, for water-free oil productive wells, arch stability can be predicated on a function of sand size, stress conditions, production rate, fluid viscosity, and formation permeability.
Selective perforation can be used to control sand movement. If a highly productive, unconsolidated sand stringer was in communication with an adjoining well-cemented section, it is possible that the unconsolidated stringer could be drained by completing the adjoining section. This method of sand control is limited in practice because of the reduced production rates realized when the highly productive interval is not perforated. Geophysical logs are the most useful tools to determine whether the selective perforating method of sand control is justified.
If rate control and the natural arching tendencies of the formation sand are unsuccessful in controlling sand production, then other methods must be considered. Mechanical methods are the most common and include plane screens, pre-packed screens and filters, and gravel packs. The plane screens include slotted liners and wire-wrapped screens. Pre-packed screens and filters consist of screens pre-packed with a filter material and porous metal filters. Gravel packing techniques consist of external or open-hole gravel packs and internal or cased-hole gravel packs. These mechanical methods will be discussed in detail in Unit 2. For now, let's state that each method has an application for which it is best suited from both an economic and mechanical standpoint.
Another method of sand control is a technique called consolidation. This technique utilizes a chemical cementing material to bond the unconsolidated sand grains together. This type of treatment requires great care so that the chemical sets up when and where it is intended. Consolidation techniques are useful in situations where a sand problem develops after a well is in production.
Whichever method of sand control is chosen, the engineer must realize that changing reservoir conditions or mechanical failure may require that additional measures be taken. This may consist of reworking or redesigning the previous sand control method. A considerable amount of information exists about formation sand failure. Whenever the use of sand control methods is under consideration, the engineer should review case histories of existing wells and utilize new technology. The material covered in this unit of the video and much more is presented in greater detail in your manual. At this time, please read Unit 1 in your manual and work the appropriate exercises. In Unit 1, we looked at a wide range of sand production characteristics and methods of control. In this unit, we'll discuss in detail the mechanical methods of sand control introduced in the first unit. We'll also take a look at their design and application. Let's start with a discussion of plane screens, beginning with slotted liners.
The slots, cut into a metal liner, must be small enough so that the formation sand does not pass through without quickly bridging off. Slot width is usually based on the formation sand sieve analysis. Generally, a slot width is sized so that 10% of the formation sand will not fit through the slot. The intent is that the other 90% of the sand will bridge off. A slot of this size has a designation of D sub 10. Field experience and filter theory have shown that sand particles greater than 1/3 of the slot size will effectively bridge off a slot because of grain interference. This same theory has been applied to hydraulic fracturing in determining the required induced fracture width that would accommodate a given size proppant during pumping. Slotted liners are more suited to medium to coarse-grained, moderately uniform sand that will quickly build up a highly permeable rubble zone around the screen. In more competent formations, bridging may be inefficient because most of the sand grains pass through the slots as they separate from the formation. This results in slot enlargement caused by sand erosion. In such wells, a smaller slot may be utilized to retain the majority of the sand grains. Slot sizes smaller than 0.012 inches are often considered too small because of the difficulty in cutting slots this size. When slot sizes should be this size or smaller, wire-wrapped screens, pre-packed screens, or filter screens are recommended. In addition to size, the slots in the liners may be positioned or shaped in a variety of ways. A common technique for reducing plugging tendencies is undercutting. Undercutting, which produces a keystone profile, is a method whereby the slots are tapered from the inside of the liner out. This tends to create bridging on the outside of the liner and not in the slot itself, where production could be reduced by the severe reduction of flow channel area. Keystone profile liners are available as small as 0.02 inches. Slotted liners may have the slots positioned vertically or horizontally. Vertical slots are more common due to strength considerations. Another kind of plane screen, the wire-wrapped screen, is a relatively low-cost sand control method. Though similar in cost and effectiveness to slotted liners, wire-wrapped screens have certain advantages that can make them preferable to slotted liners. These advantages are smaller screen size, 0.006 inches is standard, and sizes as small as 0.003 inches are available, greater inflow area, special anti-corrosive construction, greater mechanical strength when mounted on perforated pipe, and a more pronounced undercut, which helps prevent plugging. Whereas slotted liners and wire-wrapped screens are reasonably successful in medium to coarse-grained, low-strength sands when set across an open-hole completion, setting wire-wrapped screens in perforated casing often results in major problems caused by screen erosion across from the perforation before the sand bridges off.
Wire-wrapped screens and slotted liners have been successful in many conventional and thermal heavy oil wells. In general, however, they are not recommended for highly productive or high GLR wells.
Other problems can affect the success of plane screens. For example, problems experienced in the Gulf Coast have been due to fine sands plugging the screen, high flow rates with intermittent sand influx eroding the screen or liner, movement of sand and shales into the wellbore, causing a reduction in permeability, and the collapse of shale layers laminated in the productive sands, resulting in the production of solid materials called fines. A plot of formation grain size on semi-log paper indicates the percentage of sand retained at each screen size in the sieve analysis versus various sieve openings on the log scale. The selection of slot or wire screen size can be based on this plot. When experience or theoretical methods discourage the use of slotted liners or wire screens, pre-packed screens are often used. Each of these consists of an inner and outer screen. The annular area is filled with a filter material such as gravel-packed sand. The filter material is usually fused together with a plastic resin. Porous metal filters and other types of pre-packed screens are presented in your manual.
This use of sand basically serves as a downhole filter. Such filters are much more effective than slotted liners or wire screens in retaining fine sands or silts because the pore throats of the selected filtering material can be sized to as little as 15 to 25% of the grain size. In addition to the benefits of effective filtering, pre-packed filters and screens are applicable where sand production, even though small, cannot be tolerated because of high production rates, or the expense of a gravel pack is not justified.
Some mechanical problems associated with plain screens are incomplete packing on the high side of the hole in highly deviated wells, possibility of a formation slump before a gravel pack can be installed, such as in quicksands, or a limit to how close different screens can be run to each other, thus preventing independent gravel packing, such as in closely spaced intervals. Care must be exercised so that no damage is induced while running the screens through the BOPs, wellheads, and other equipment. Since a screen may need to be replaced, its size should allow washover operations to be conducted. The screen installation should also include centralizers that can be washed over. Centralizers are usually spaced about 15 feet apart.
Now, let's turn our attention to gravel packing, the most common and generally most effective method of sand control. As mentioned before, there are two basic types of gravel packing, the open-hole gravel pack and the cased-hole gravel pack.
In the external or open-hole gravel pack, the casing is set above the pay zone, and the open-hole wellbore is then under-reamed to maximize flow area. The gravel pack screen is hung as an uncemented liner, and the area between the screen and the formation is packed with the appropriately sized gravel. When a zone behind casing is to be externally gravel packed, milling of the casing is necessary before the under-reaming can be done. The internal or cased hole gravel pack does not require any special drilling. It does require perforation of the subject zone with a high density of large diameter, deep penetrating holes. The damage caused by perforating is cleaned out as completely as possible by backflushing, washing, or underbalanced perforating. The key to an effective cased hole gravel pack is to, first, create a cavity beyond the cement and damaged formation, and then pack this cavity from the undamaged reservoir through the perforated casing and into the casing screen annular area with a high permeability gravel.
Due to improved methods of squeeze packing and perforating, the internal gravel pack is the most widely employed technique. Overall, a properly executed internal gravel pack offers greater flexibility, selectivity, planning time, and reduced rig time and cost than other methods.
In any gravel pack design, the gravel size is crucial. Improperly sized gravel can result in severe reductions in permeability. Over the years, recommendations about gravel size have changed significantly. One widely accepted method of determining proper gravel size was presented by Saussure.
The accepted rule, based on the Saussure method, is that the median gravel size should be slightly less than 6 times the median sand size.
The high quality of gravel pack material is essential, and quality control must be employed. Specifications of gravel pack sand have been outlined in API Recommended Practices number 58. The most common and effective method of gravel placement utilizes a piece of equipment having a setting tool crossover assembly and a lower extension assembly that includes a screen. Almost every phase of drilling and completing the pay zone will affect the success of a gravel pack. Basically, current methods of gravel packing are based on the principles of retention-type filtering. This kind of filtering does not allow mixing of formation sand with the gravel pack material, and, in the case of internal gravel packs, prevents sand encroachment into the perforation tunnels. In designing a successful gravel pack, the engineer must consider the following 5 main areas of concern. 1. Proper selection of gravel and screen. 2. Clean, high-quality fluids and gravel. 3. careful hole preparation, gravel placement, and cleanup. 4. The use of proper tools and procedures. And 5. The application of current techniques and design methods.
The cased hole gravel pack is the most common method of mechanical sand control employed during initial completions for light to medium producing oil and gas wells.
Let's look at cased hole gravel pack design using Baker Sand Control's full-scale gravel pack simulator. Such models provide us with a means of understanding the effect of perforations, gravel size, screen choices, reservoir heterogeneities, and fluid composition on the gravel pack.
The reason we've built the gravel pack simulator is to allow us to get an idea of how gravel is actually placed downhole in differing types of reservoirs. We've done simulations for various operators all over the world to take a look at unique circumstances that occur downhole. For example, what happens if you have an extremely mixed lithology formation where you have numerous shale breaks in the formation in addition to both high and low permeability intervals. Now, we control the rate of leak-off to each perforation by the combination of the permeability of the core material itself plus the manifold system, which we can hold back pressure on the perforation tunnel. Since it's so important that we fill the perforation tunnels with gravel, this is something that is very, very difficult to visualize what's exactly actually happening from the surface. So this gives us a good idea of what to expect when we go to the field. And these designs have been tried in the field. We can vary things like the actual screen size, the wash pipe combination, the gravel pack method. Do we circulate the gravel pack in place or do we squeeze the gravel into the formation? And vary things like the polymer concentration, the sand concentration, and the actual pump rate that we use when the gravel is placed. The combination of this, I think, makes us smarter in the end, and we can actually take what we've learned in the laboratory on a laboratory device and try and apply this to the real world in the field. So although the simulator itself has limitations of sorts, we are definitely a lot smarter for having it than if we didn't have the mechanism for actually trying to visualize it. We've oriented the model in a vertical position today and attempted to do a gravel pack that fills up both the annular space around the outside of the screen as well as the simulated perforations. We have 12 shots per foot of perforations on here, and when we experience a high rate of leak-off, as we did today, we can sometimes run into problems with the gravel placement in the annular space. So what we observed happen was the yellow pre-pad moving down, filling the perforated interval, leaking off into the simulated formation, as well as circulating down and through the end of the wash pipe and through the screen. When the sand slurry came into the model, however, we experienced a high rate of leak-off into the formation. The sand bridged around the perforated interval up at the top of the screen and ultimately reduced the flow area to the extent that we experienced a bridge at the very top of the screen itself. This prevented the annular space below about the 12-foot interval from filling completely with sand. With time, we've observed that the sand has settled out and has filled up the majority of the void, and in the field this would have normally been okay in such a short model because we would have had a sufficient reservoir and blank area above the top of the screen that was containing gravel. Had we had a much longer perforated interval, I'm not sure that we can count on having enough blank interval to allow for that much settling to occur and to fill the zone. So although the gravel pack was not performed in the ideal manner, in this particular case it would have been successful.
Now that we have discussed some of the concerns regarding gravel placement, let's consider the flow of reservoir fluids through the packed area and into the wellbore. The greatest pressure drop generally occurs where the produced fluids flow through the perforations. This pressure loss in the perforation channel is due to the convergence of the produced fluids from radial flow into a linear flow pattern. Darcy's linear flow equation demonstrates the importance of placing a highly permeable gravel pack in the perforation tunnel. Looking at Darcy's equation, it is apparent that the pressure drop will decrease by increasing the perforation area. Therefore, perforations should be as large and as densely spaced as possible. Mechanical and economic factors limit the optimum size and number of perforations. Generally, perforations 3/4 to 1 inch in diameter, with a density of 8 to 12 shots per foot, are considered the maximum for a cemented string of pipe. Many engineers believe that provided the casing is securely cemented and the pressure differential between the casing OD and ID is not great, such high-density perforating should not cause casing failure. It should be noted that permeability will be reduced and a greater pressure drop will occur where formation sand mixes with the gravel pack. Thus, the gravel-formation sand interface should be placed as far from the perforation tunnel as possible. The selection of gravel size should be based on its ability to, first, control the production of formation sand, and second, achieve maximum permeability. As shown in this table of the measured permeabilities of clean gravels, with calculated pressure loss through a 3-inch long, 0.8-inch diameter flow channel, the pressure loss through all these common gravels is insignificant. In addition, most gravel pack material has a permeability much greater than the formation. Thus, gravel is generally sized, again using the Saussure method, primarily on the size of the formation sand. Selection of a screen should be made with the primary aim of preventing the gravel pack material from flowing through the screen. Two common methods of determining screen openings, which yield approximately the same results, are to size the openings either slightly smaller than the smallest gravel size or 1/2 the mean gravel size. Pressure loss through the screen is generally minimal, provided the screen is not plugged with fines.
The correct placement of a screen of proper length, diameter, and composition is essential. The length of the liner screen should be sufficient to cover the producing formation. Internal gravel packs are limited in length. Some operators limit these packs to 150 to 200 feet, especially in deviated wells. Where longer intervals are completed, operators stack separately placed 100-foot packs. It should be noted that open-hole gravel packs have historically proven more successful in thick intervals.
The diameter of the screen should be appropriately sized to enable gravel placement in the screen casing annulus without bridging problems. An annular space of at least 1 inch should be provided around the screen and inside the casing. The tubing and screen are generally the same diameter in single-zone completions.
Let's keep these considerations in mind and look at the design of a cased-hole gravel pack. The interval to be completed has been cored and the analysis results have been given for the 20-foot sand.
In this example, the sieve opening that will contain 50% of the formation sand is 180 microns. Based on the Saussure method, the desired gravel should be 6 times 180 microns, or 1,080 microns. This table of common sieve sizes indicates that a 1630 mesh gravel would be appropriate. However, since a 1630 gravel is not readily available, 1220 gravel is selected instead. 12 mesh gravel has an average grain diameter of 1700 microns. 20 mesh gravel has an average diameter of 850 microns. Based on the average diameter of the smallest gravel, the 20 mesh, a 20-gauge slot would be appropriate. It is preferable to size the screen and gravel material slightly smaller than the optimum size calculated, rather than larger, to avoid the damaging effects of sand production and the resulting significant reduction in permeability if the formation sand and gravel are mixed. In light of this, a 2040 mesh gravel and 12-gauge screen may be a better choice, especially since the pressure drop in 2040 gravel would result in only a slightly greater pressure loss compared to the 1220 gravel. Darcy's linear flow equation is used to calculate the theoretical pressure drop under these conditions. To illustrate this, we will calculate the pressure drop through perforations packed with 2040 mesh gravel and 1220 mesh gravel, with permeabilities of 120 and 300 Darcy's respectively. Each perforation is producing 9.375 barrels per day. Assuming values for the remaining variables of fluid viscosity, perforation flow channel length, formation volume factor, and average entry hole area, the pressure loss can be calculated. As shown by these calculations, the pressure drop for either pack would be less than 10 psi. Quite insignificant. To further illustrate this major point, let's calculate the pressure loss if the perforation channel were filled with formation sand with a permeability of 500 millidarcies. Using Darcy's flow equation, we calculate a pressure drop of 1710 psi. This pressure drop certainly is significant and would prevent the production potential of this well from being realized. This simple example, combined with our previous discussions of perforation area and density, demonstrates the importance of the following basic requirements. Properly sized gravel that will not allow migration of reservoir sand into the gravel pack. Large diameter entry shot of the perforations, and a high density of perforations per foot. In addition, clean completion fluids are essential to optimize perforation flow area and gravel permeability. These basic requirements also indicate why an open-hole gravel pack is preferred in highly productive wells. This same approach can easily show that a 2,500 psi pressure loss would occur if a 4-inch diameter wellbore, producing 1,500 barrels of fluid per day with a viscosity of 1 centipoise, had a 10-foot sand bridge with a permeability of 61 darcies.
This unit covered only the mechanical methods of sand control, those being the most common. The other methods of sand control have been presented in detail in your manual. In the next unit, we'll review the equipment used in gravel packing. For now, please read Unit 2 in your manual and work the appropriate exercises. In this unit, we'll discuss the downhole and surface equipment used in a gravel packing operation. This includes the downhole tool assemblies as well as the surface pumping, blending, and filtering systems. As mentioned in Unit 2, the technique of gravel packing is the most common method of sand control. In light of this, our discussion of downhole tools will deal only with the equipment and procedures associated with gravel packs.
Again, it is emphasized that fluid cleanliness and quality is essential. Any tools that enter the wellbore, including casing and tubing, must be free of rust, scale, and other debris. The downhole tools must be inspected to ensure that they work efficiently in order to minimize the risk of tool failure and the number of trips in and out of the well. A work string should be used in order to prevent wear on the often lighter production tubing. The work string should be cleaned thoroughly before use. Conventional cased hole single zone gravel pack operations use tool assemblies like this one, which is run on the work string. The particular tool shown here enables acidizing and high density gravel packing in one trip. The usual downhole components of a gravel packing operation are included here. Let's review the components, beginning immediately below the work string with the setting tool crossover assembly. The setting tool crossover assembly is secured to a packer. During running in and squeezing operations, the bypass port in the crossover tool assembly is positioned within the packer. Slips secure the packer to the casing. Below the packer is the perforated extension. As shown in the disassembled tool string, the perforated extension contains the crossover tool assembly and its gravel pack port, through which gravel is pumped into the extension and out the perforations. Below the perforated extension is the seal bore sub, and attached to it is the lower extension. The indicating ring on the setting tool crossover assembly, just above the wash pipe, forms a seal against the seal bore sub during gravel packing. A crossover sub and shear-out safety joint are attached to the lower extension. Below the safety joint, a length of blank pipe is run that is usually 3 times the length of the screen. Centralizers are necessary to facilitate proper gravel placement in the screen casing annulus. The wash pipe runs inside the blank pipe and gravel pack screen. At the bottom of the screen are the lower centralizers, the O-ring sub, and the telltale screen. The wash pipe extends into the telltale screen. The wash pipe and the gravel pack assembly will be pulled from the wellbore following the gravel pack operation. Attached to the telltale screen is another crossover sub. The locator and seal assembly are run down to the sump packer, which has been previously installed by wireline. At the bottom of this wash pipe is a multiple-acting indicating collet, which gives a positive indication to the rig hand that the seals are in the sump packer. The tool string is run in and readied for circulation. The setting tool crossover assembly, attached to the upper end of the packer with a left-hand thread, is sealed off between the packer and the seal bore sub. The gravel pack port is positioned inside the perforated extension, also between the packer and the seal bore sub. The wash pipe extends from below the setting tool crossover assembly to near the bottom of the telltale screen. At the setting depth, the tripping ball is circulated or gravitated into place on the ball seat. Applying pressure will actuate the setting tool, causing the packer slips to engage the casing and the element to pack off. Increasing the pressure will shear the ball seat, opening the gravel pack port. After setting the packer, the setting tool crossover assembly is released from the packer with right-hand rotation. Circulation for the placement of acid and gravel is accomplished by raising the setting tool crossover assembly until the indicating ring contacts the lower end of the seal bore sub. In this position, the bypass ports, located below the top seal of the setting tool assembly, are above the packer bore and open to allow for circulation and gravel placement. After the gravel has been placed, the setting tool crossover assembly is lowered, closing the bypass ports. While in this position, returns are shut off and squeeze pressure is applied to further consolidate the gravel pack. Application of upstrain releases the indicating ring, permitting further upward movement of the setting tool crossover assembly into the reversing position. In this position, the wash pipe is above the O-ring seal sub. The lower seals of the setting tool crossover assembly are above the seal bore sub, and the seals above the gravel pack port are still in the packer bore. Fluids circulated down the annulus enter the bypass ports above the packer, flow down the wash pipe, and then up between the wash pipe and screen and into the gravel pack port. This reverses out any excess gravel from the work string and cleans any debris from inside the screen.
Note that when gravel packing low bottom hole pressure wells using the setting tool crossover assembly, reversing pressure is exposed to the formation. This adversely affects the ability to reverse excess gravel from the work string and may lead to formation damage.
In order to avoid this problem, this setting tool crossover assembly can be modified by running the tool with a circulating ball in place at the bottom end. The job procedure remains the same except for the reversing sequence. When the gravel pack is complete, the work string is raised until the gravel pack port is above the packer. In this position, seals remain in the packer bore and reversal is accomplished above the packer. Upon completion of reversal, the setting tool crossover assembly is removed and a locator seal assembly is run on the completion tubing string. The locator seal assembly seals off in both the seal bore sub and packer bore. The perforated extension is therefore isolated, permitting the well to be placed into production.
There is a wide range of cased hole gravel pack assemblies available. Multiple completion intervals, thick intervals, and deviated wells are situations requiring special considerations and often special types of gravel pack assemblies.
The open-hole gravel pack employs the same conventional circulation techniques. Like the cased-hole gravel pack, this system allows the implementation of a circulating gravel pack around a slotted liner or screen. One advantage of this particular tool assembly is that the gravel pack operation can be performed with a lead seal adapter in place on the assembly, thus eliminating the need for an extra trip to install the lead seal assembly. This assembly is also run on a work string. Below the work string is a bumper sub and the down cup tool for adapter port collar combination. The lead seal adapter is positioned below the down cup tool. The lead seal adapter remains in the well bore and serves to retain the gravel pack material. The gravel pack tools below the lead seal adapter are the 2-cup straddle tool, the port collar, and the check valve. All are necessary to ensure the proper flow of fluid. The sand-laden fluid is pumped down the work string and flows out the gravel pack port, through the port collar, and into the open hole outside the screen. Fluid returns through the screen, into a slotted bull plug, up the wash pipe, through the check valve, and the 2-cup straddle tool, out the lower bypass port, then into the down cup tool, out the bypass port, and up the tubing casing annulus to the surface. Upon completion of the gravel pack, circulation is established down the casing work string annulus, through the bypass ports, into the gravel pack port, and up the work string. This reverses out any excess gravel. Following the reverse circulation, the work string is right-hand rotated to release the preset prevention mechanism in the lead seal adapter. The application of weight, or impact, to the work string packs off the lead seal, forming a positive liner casing barrier to prevent gravel migration. Additional right-hand rotation releases the gravel pack tools from the lead seal adapter. Next, the work string is raised in order to position the turning tool inside the port collar. Right-hand rotation closes the port collar, providing complete isolation of the gravel pack. At this point, the work string and down cup tool are removed from the well bore, and the well is ready to be produced.
Let's review the surface equipment generally required to perform a gravel pack operation.
The surface equipment required for the operation generally includes blenders, triplex pumps, and filtration equipment. All surface equipment must be clean. No rust, sludge, or debris should be on any part of the equipment that may contact the treating fluid and contaminate the gravel packing fluid. The blender used to mix the gelled fluids is often referred to as a paddle blender, owing to the paddles used to mix the chemicals and gravel material. This equipment should be internally coated with plastic or other non-corrosive material and must always be cleaned prior to use to prevent contamination of treating fluid. Centrifugal pumps transfer the fluid at low pressures into the blenders and displacement tanks. The power pack provides the necessary hydraulic horsepower to operate the centrifugal pumps. The prime mover is usually a diesel motor and, in conjunction with a hydraulic pump, provides an independent variable control for each hydraulic motor. Filtration of the treating fluids is a critical concern when gravel packing. Any fluids used for gravel packing should be filtered, first when stored and again after mixing the gel. Filter systems may be of the cartridge type or diatomaceous earth type. Cartridge type filters are generally capable of filtering out particles of 2 microns. Diatomaceous earth filters can remove particles of less than 1/2 micron. To visually put this size in perspective, a human hair ranges in size from 10 to 40 microns. Even smoke particles are larger than 3 microns. The triplex pump and the equipment associated with the pumping unit are the most important pieces of equipment on location during a gravel pack operation. This unit is powered by a diesel engine delivering over 400 horsepower. Each has a maximum working pressure of 10,000 psi and a maximum flow rate of 10 barrels per minute. Located on top of this unit is the operator's control station. Here, the pump displacement and operations are controlled and monitored throughout the job. Treating pressure is closely watched to ensure that the pressures remain within design parameters. Treating pressure and rate are permanently recorded. The service company must also closely monitor the displacement tanks, in this case 2 calibrated 10-barrel tanks which hold the sand-laden fluid pumped from the blender. Special care should be taken to ensure the cleanliness of the pumps and associated equipment. Triplex pumps used for cementing operations should not be used for gravel packing because cement additives can be very damaging. Equipment chosen for the job should be specially designed for gravel packing operations. The metallurgy and design of the triplex pumps should be discussed with the service company prior to the job. Pumps which limit crushing of the gravel pack material should be specified. The tanks used to hold the treating fluid must be clean and contain no damaging chemicals. Analysis of the treating fluid using a turbidimeter should indicate not more than 20 to 100 parts per million total suspended solids, depending on the formation. The treating fluid must be compatible with the formation so that no damage will be caused by swelling clay material, scale precipitation, or emulsions. The addition of a gelling agent to the treating fluid is required to achieve the viscosity necessary for transporting the gravel pack material. The ideal fluid should control formation pressure, clean the hole, wash the perforations, carry the gravel to the formation, and enable the gravel to be packed against the formation and screen. After the gravel has been placed, the viscosity of the gelled treating fluid must break down to a consistency that can be flushed out of the wellbore. The solids remaining after a gel has broken down in the formation can be very damaging. Care must be taken to use a gel with a low percentage of residual solids. A premium grade of hydroxyethyl cellulose, HEC, has been tested and shown to have only about 0.15% residual solids after the gel has broken down.
Historically, the selection of gelled fluid systems have been based on the ability to transport the gravel at concentrations of approximately 15 pounds per gallon. Some engineers now believe that a slurry of only 4 or 5 pounds per gallon may make a better, more tightly packed gravel pack. Although this lighter slurry requires greater fluid volumes and more chemical additives, if field practice proves this method superior, it may become standard. Gravel packing technology is continuously being evaluated, and engineers must stay abreast of current development, as well as study historically proven practices, to hypothesize the most effective treatment. The selection of chemical additives to prevent formation damage must be based on tests of the formation sand and fluid and the treating fluid. Often 2% potassium chloride by weight is added to control the swelling of clay material. The reservoir and treating fluid composition should be chemically analyzed and additives used as necessary. The selection of a compatible treating fluid will preclude the need for most chemicals and will reduce costs and risks of damaging the formation. Sand control is both a completion and workover technique that is necessary in many of the more prolific reservoirs throughout the world. It must be emphasized that due to the natural high productivity of these wells, the primary objective of sand control is to prevent sand production, not to stimulate the well. The engineer does, of course, want to maximize production, and this can be achieved by exercising strict quality control measures and selecting the optimum sand control method based on careful testing and experience. At this time, please read Unit 3 in your manual and work the appropriate exercises. Good luck.